Welcome to GSA Connects.
Welcome to GSA Connects.
Welcome to GSA Connects.
What is going on in geoscience right now? What kind of research is being conducted? What kind of questions are being investigated? Hello, my name is Rachel, and I am currently one of GSA's Science Communication Fellows, which means that I'll be popping on here on the GeoSociety channel a little bit more this year to share a lot of the work being published in their journals, the work being presented at their annual meeting, and that's what you're watching right now. I also have my own channel called GeoGirl, where I share a lot of geoscience content as well, so I will link that in the description box of this video if you're interested in checking it out. And with that, we'll get back to today's conversation. The Geological Society of America, or GSA, hosts a huge conference every year called GSA Connects, where geoscientists come together to share their research and talk about the remaining questions in pretty much every field of earth science that you could imagine. Research shared at this meeting is either presented as a talk or a poster. I find the posters super cool because you get to have one-on-one conversations with the people that come to your poster. And sometimes these can even help you decide future directions for research. I just got back from this year's GSA Connects 2024, and I wanted to showcase the diversity of research that was presented at this conference. So I made this compilation of a bunch of poster presentations that I got to record while I was there. Although you should note going into this that it barely even scratches the surface of what's presented, but at least it may give you an idea of what goes on at these conferences, what kind of work is being done, and maybe in the future, if you want to go present your work at next year's meeting, you'll know what to expect. So we'll jump right into the presentations I got to record, starting with Kaylee Long from Fort Hays State University, who had a presentation about a Minecraft museum she designed, showcasing Triassic animals, including dinosaurs. So let's get into it.
So the project that I have here is a virtual museum made on a modded instance of Minecraft. So my museum compares animals from the Triassic to animals in modern times, comparing their morphology and ecology. And so once the museum building itself is ready, we will actually be removing all of the Triassic animals from their enclosures, and visitors to the museum will instead be sent back into the Triassic to go on a collection mission to actually collect all of the animals needed to be put on display. And so they will actually explore the past environments of the Triassic, set out traps with food to catch the animals. So let's see if the internet is on our side today. And so right here, we have the Lystrosaurus enclosure, modeled after a floodplain in the dry season.
That is so cool.
And they are being compared to boars, and their environment is a deciduous temperate forest.
Wow. Is this like out? Is this being used by people?
Not yet.
Okay.
Like I said, the project is in its infancy.
Oh, okay.
The museum building itself is very much not done. That is because it actually took 7 weeks to get this server just to start up and work.
Oh,
So all that time I wanted to spend building was spent just getting the mods to work.
oh wow.
Here we have the Coelophysis enclosure in the floodplain during the wet season.
This is so cool.
I don't know if you heard that, but the Coelophysis just hissed at us. And here's the cassowary enclosure, modeled after New Guinea rainforest. So yeah, big Minecraft builds like these usually take 1 or 3 years to fully complete, even if you have paid staff helping you.
Yeah.
Right now it's just me and 2 other people,
Yeah.
but I do plan to get this up and running. And once the museum building itself is done, I'm going to be doing some test runs, getting this save file along with the mod pack out to maybe some schools for them to test to see if students are going to have fun with this model, and if they are able to learn more about prehistory using it. And hopefully I'm going to be paired up with a museum, because the plan after I graduate is to work at a museum. And so if I can get a museum helping me build this and distribute this, that would be the dream.
Yeah.
And so I'm just very passionate about paleontology itself. If I can make learning about past environments and all the organisms that live in them more fun, I absolutely want to do that.
Wasn't that incredible? Kaylee's was one of my favorites. I never even thought of doing like a Minecraft museum like that to help, kids learn about Triassic and other ancient life. That's so cool. Anyway, next we have Demi Durham from Trinity University talking about faults on Mars.
For the past few months, I've been looking at the circumferential fault system surrounding Alba Mons on the western flank. The fault system propagated over 4 stages, and the most important of these 4 stages is the third one, where we see extrusive volcanism that Alba Mons' summit dome relaxes, in which there's lithospheric flexure that occurs. So alba fossae forms to accommodate for that extension in the region. And we see that there are 2 volcanic lobes on either side of the volcano, with the western lobe being much bigger than the eastern lobe. And the western lobe features a noticeable slope break here, or here on this picture. And previous researchers thought that this slope break has something to do with the initiation of alba fossae and the circumferential fault system. But since we have this amazing 200-meter DEM that's newly published, we can see that alba fossae is actually located on the summit dome of the western lobe. So it's not likely that the slope break has much to do with the influence or initiation of alba fossae. So in the future, we're planning to look into the magmatics of the western lobe of alba fossae, and more specifically dike intrusions. And we also plan to continue to look at pre-existing stress fields and weaknesses of the volcano to see the true evolution of the fault system. The biggest reason we care about faults on Mars is because there's no atmosphere, so there's no erosion and there's no vegetation, which means that basically these are untouched by nature, unlike we do have on Earth. We just don't have these types of analogs on Earth, and these images allow us to basically measure things that we would not be able to in the first place. And also Mars has no plate tectonics, so this is mostly due to gravitational or lithospheric flexure. But since we do see those patterns and we're kind of confused by them, that's why we want to look deeper into what's happening under the surface.
Next, we have Julia Shreve from Grand Valley State University talking about how prescribed sheep grazing can help soils sequester more carbon.
My research is focusing on land management strategies, specifically prescribed sheep grazing that can be a significant role in carbon sequestration and a response to mitigate climate change. And I'm more focusing on 2 soil organic matter fractions, POM, which is particulate organic matter, which is plant matter. It decomposes a lot faster, is less stable. And then the mineral-associated organic matter, which is when carbon actually clings onto those mineral grains for decades or even centuries. So why we care about that is because we want to hold that carbon from the air back into the soil and keep it long-term.
Next, we have Naomi Wurtzel and Sam Doza from the University of Puget Sound talking about restoring salmon habitats.
So salmon are a really important species in Washington State and the U.S. So we were looking at a newly restored salmon restoration site in the Puyallup watersheds, South Prairie Creek. What we were doing is we were taking macroinvertebrates and vegetation samples and conducting a stable isotope analysis of carbon and nitrogen to determine if marine-derived nutrients, so if salmon had returned to the restored site. The carbon essentially tells us what things are eating, and then the nitrogen sort of tells us the trophic level. So we can see like the trophic increases between the different ecological functional groups of the macroinvertebrates and how the salmon is impacting that.
So what we found is that salmon are using this habitat, which is a good sign and a good indication for future restoration work at the site. Predators who are likely eating these dead salmon, they do reflect this trend of close to the salmon values and then going along this to the vegetation habitat.
Next, we have Walker Wayland from Harvard University talking about Ediacaran biota, these very early multicellular organisms that were potentially the very first animals on Earth, which lived around 600 million years ago. And he talks about what he found regarding the feeding behaviors of 2 Ediacaran species.
So here we're looking at some Ediacaran fossils, which occurred just before the Cambrian. We have 2 species, Dickinsonia in the center and some Sphryginomorphs around the sides. And what we found is the Sphryginomorphs are sort of mooching off the hard work of the Dickinsonias. The Dickinsonias are going around eating the microbial mat, but they're messy eaters and leftovers are flying all over the place, and the Sphryginomorphs are eating those leftovers.
Next, we have Melody Green at Ohio State University talking about the impact of climate change on scenic rivers in Ohio.
So I looked at scenic rivers in Ohio. I looked at the Grand River and the Darby River, and I looked at long-term regional changes in the discharge of the rivers. And I compared that to precipitation to see the climate changes over time and how they impact discharge. And then here we have the discharge against precipitation, and we also shaded the El Nino and La Nina regions that were stronger than a 1.5 degree change anomaly. And so what we saw is an average increase in discharge for the Grand and the Darby River. Here are the monthly discharge linear trends, and we also see an average increase here for 8 months out of the 12. And so what my research shows here is that the climate is impacting these two rivers, and it's increasing the discharge over time, and this could be due to a lot of different factors and could have some anthropogenic influences as well. But it does show an impact on rivers that, for me, are close to home and are areas that, you know, lots of people live around and can impact people's homes and the areas around them. And it's something that is really important when we're looking at climate changes over time.
Next, we have Bryn Wooten at Vanderbilt University, who studies how ancient mammals have been affected by climate change so that we can better understand how modern mammals might be affected by climate change.
And I was interested in how climate and environment data is recorded in the teeth of macropodids, so kangaroos and wallabies. We looked at two different variables. So we looked at dental microwear, which you can see here, which is like the pits and scratches in teeth that record diet. We know they record diet, but we were interested if they might also record some climate or environment variables. And then stable isotopes, which we know record climate. So we found that dental microwear does not record any climate or environment data. It's just strictly diet, which is what we expected. And then, as also we expected, stable isotopes are being recorded, are recording climate data. Our data was collected both manually and with a GIS. So we were also interested in whether those two different collection methods would give different results. And for the most part, they were similar, except for mean annual precipitation, which is also weird because this has a positive correlation, and we would actually expect a negative correlation in this specific relationship. So we were thinking about why this might be. And the swamp wallaby has been seen and has stomach contents proving that they eat fungus. So we think that this is actually a positive correlation because they're eating fungus, which are approximately 3 per mil higher than surrounding vegetation that they could be eating. And the main purpose of this is, like, if we research modern mammals, then we can apply that to paleo mammals. And then we can apply that back to modern mammals to understand how they might react to climate change.
Next, we have Joseph Bingham from West Virginia University, who studies one of my personal favorites, sea scorpions, or eurypterids.
So, I'm currently studying the early evolutionary history of eurypterids. Eurypterids are a group of telistid arthropods that first appeared during the Middle Ordovician and went extinct at the end of the Permian. I'm describing two new species of eurypterids from the Big Hill Loggershot found in the Stonington Peninsula of Michigan. My sea scorpions, my eurypterids, are very closely related to both Cysophora, which are horseshoe crabs, and to arachnids, scorpions, spiders, and the like. And so in investigating their evolutionary history, we are also, in a way, investigating the evolutionary history of those extant groups. And so if we find out stuff about them, we can find out stuff about those groups as well.
Next, we have Sophie Barnett from the University of North Carolina, Charlotte, who studies how trash affects ecosystems in her state. And she's also working really hard to get fast food chains and franchises in her state to move away from plastic and toward paper products.
I'm a garbologist by heart, but I'm a hydrologist by training, and I study trash deposition and floodplains in urban restored systems. With that being said, the ultimate goal of my graduate research is to build a large-scale model where I can predict different landscape factors versus hydrometeorological factors to see how they influence trash accumulation in floodplains. I have densities such as the grocery density, fast food density, big box provider density, and my favorite density, the vice density, where I count all of the vape stores, ABCD stores, bars, strip clubs in a nearby area, and I determine whether or not they influence trash. And what do you know? Wow, they have a p-value of 0.001, so they do significantly influence trash. I also am doing novel research. No one actually categorizes where trash is found in a floodplain, so I categorize it whether or not it's buried in sediment, cotton vegetation, or freestanding. The majority of the trash is found freestanding, but with that being said, if we go over here, you can see that this is an example of a tree that is in one of my floodplains. There's 13 pieces of trash stuck in this tree. So obviously that's impacting the tree's ability to uptake oxygen and other things. In addition to that, I also have proof of vegetation growing into soft plastic and cardboard. So right here, this is a Virginia creeper, which is a very prolific and adventitious vine. It grows anywhere it wants to. And I pulled on this, and the roots were literally growing into trash. Obviously, it's uptaking microplastics in some capacity. And in addition to that, I have also found evidence of trash melting into rocks. So right here, you can see that this is a piece of what I think it is tar. I'm not sure yet. And it basically got deposited in this tree. It's stretchy right here. It melted down onto this rock, and I peeled it off, and it still has deposition there. And there's currently one study about plastics in the Anthropocene, where basically when plastics get buried in sediment, they can melt into rocks. But this is something that's also very interesting, and it needs to be researched more. My floodplains vary by vegetative cover. For instance, one of mine is Toby Creek. And during the spring and summer, there's very high growth vegetation. I have to take a machete and cut down on the vegetation to be able to go and even get to the river. So I'm obviously undercounting trash. But I also think that it means that there's a lot more trash storage in this area. I also take all of the brand identification for identifiable pieces of trash. So my hope is that I'll be able to go on a one-on-one basis to people who own stores in the Charlotte area, right? You go to McDonald's, it says it's owned by so-and-so. So I hope that I'll be able to somehow convince them to switch to paper products, because in California, where we are right now, you go to McDonald's and you buy a soda, it's going to give it to you in a paper cup. In North Carolina, it's going to be in a plastic cup. It's cheaper to produce plastic than it is to produce paper, but paper is able to biodegrade. One day, I want to be a professor, and I want to be able to fund an NSF study where I'd be able to determine and do this modeling in multiple cities, in urban and rural watersheds, to be able to really test my model. But for now, I am just continuing my master's research. And overall, from the past 2 years, I have removed 1,563 pounds of trash from the Charlotte-Mecklenburg area.
Can we just take a moment to appreciate that? Over 1,300 pounds of trash that she's removed.
Okay, now I'm going to talk about my soil sediments. So somehow I brought my soil sediments through TSA, because there's smart people here who might tell me how to identify the microplastics better. So if we look right here, you can see that I have two filters, and they are brown in color. However, you can see that I have a bunch of these little tiny black pieces on these filters, right? So I took the diamond tip of the FTIR machine and I touched it to it, and it says that it's polycarbonate, which is a type of plastic. This one is a 25 micrometer sieved sample, and you see that one piece right up there at the top. All of these, there's so much pieces of polycarbonate prolifically mixed into the soil matrix of the first 5 centimeters. It's very scary, to be quite honest with you. It means that we are ingesting plastic, and our plants and our fish, everything is ingesting plastic.
Next, we have Ophelia Peddington from Missouri State University, who's looking at the microbes present in mining contaminated and remediated soils.
Hello, my name is Ophelia. My project focuses on bioremediation of metals and contaminated soils in the Tri-State Mining District. I am hoping to find that there is a relationship between plants and microbes that are helping these plants survive in this contaminated soil. There are several bacteria that help remediate, and it has also been shown that sometimes these plant-microbe interactions do help with plants to tolerate those metals. We're still in preliminary stages. I just completed field work. I only really have the physiochemical characteristics of the soil. I am about to send off my DNA for microbial analysis. We are focusing on bacteria specifically, so we chose a gene specific to bacteria that will allow us to look at the entire community down to species level. I am working with the U.S. Fish and Wildlife Service, and they just acquired new land that is contaminated with zinc, just like my projects. So we're hoping that we can find a certain bacteria that is already remediating in this area. Because soil varies so much from place to place, it's best to find a native bacteria that is already remediating, or a native symbiotic relationship that's already happening, so that you can use that in a new site via planting these plants or by inoculating with a specific bacteria.
These do tend to be more cost effective than the traditional physical remediation methods, but we're hoping that they can either be combined or used independently.
Next, we have Jen O'Keefe from Morehead State University, who led a project that was worked on primarily by undergrads, which is super exciting, looking at fungal microclimates in soil. In other words, how the climate where fungi live in the soil is different than the climate above ground. I mean, how cool is that?
Hey, hi, I'm Jen O'Keefe. I'm leading the Fungi in a Warmer World project. 4 years ago, we set out to develop a new paleoclimate proxy using fossil fungi because they capture ground level, near surface, and near subsurface microclimate in a way that few other organisms do. They're also one of the foundations of our terrestrial ecosystem. They're drivers of carbon cycling. They are our plant symbionts. Okay, if we don't have the fungi, we don't have our crops and we don't have our trees. That's a big problem going forward. So here, 4 years into the project, we're able to, for the first time, to reconstruct ground level microclimate. What's interesting in this particular site is that when we look at the pollen, the whole pollen spectrum plots warm. The pollen just from this particular area, excluding the upland taxa, reconstructs cooler. And when we pull the fungi in, the fungi reconstructed using the same methods as the pollen plots even cooler. So we're capturing a much, much cooler ground surface level than an atmospheric temperature. So this suggests that the fungal community changes we're seeing today are tied very closely to local ground level changes, and that the overall atmospheric changes are perhaps less important than what's happening on the ground. And we've seen hints of this in a lot of the work, but no one's ever been able to show this in the ancient past before, which provides huge implications for ground surface microclimate effects on fungal community change with climate change.
Next, we have one of my personal favorites, Evan Chang from Yale, who studies paleontology and paleo art and did a summer project combining those two passions to create something super cool. But I'll let him explain.
Hi, so I am Evan Chang. I am an invertebrate paleontologist and a ceramicist. And this was my project Permian Summer, so it's a summer project. I made this in collaboration with Kelsey Jenkins, who is a vertebrate paleontologist at the Smithsonian, because I'm not a vertebrate paleontologist. And so she introduced me to these Permian tetrapods, and they're like kind of the most iconic creatures of the Permian. And they were doing really well during the Permian because the Carboniferous rainforest had collapsed. And so the amphibians that diversified during the Carboniferous weren't doing as well, but the reptiles and mammals were, or the early reptiles and mammals. And so a lot of them evolved to great sizes, distinct morphologies, and so you have kind of what you might see in natural history museums a lot, Dimetrodon, Edaphosaurus, and they have this iconic big sail in the back that we think was used for heat regulation. But you also have some fossils that I didn't know about, like Coeloceravus, which had these wings on the side that it would extend out to glide, like modern gliding reptiles.
I didn't know about that.
And so I thought about all of these really interesting morphologies on these species that we know a lot about. But there are still some things that we don't know about. For example, what color they might be, or how on their bodies their flesh might have bulged out or curved in. And we also don't know how they sounded, for example. But if you kind of broaden it out, think about all of the lineages of animals that are lost under some formation somewhere in the world, or never got a chance to fossilize. They rotted away or predated upon, or maybe they did fossilize, but they were eroded after a couple more millions of years. And so if you think about it that way, then you've got an infinite unknown. And it's this infinite unknown that drives paleontologists like me to do the work that we do, but it's also what drives non-paleontologists to be fascinated by these ancient fragments of bone that we will never see. We will never know what they look like. We will never hear them, see them, but we're just so fascinated by them. You know, when I think of an ancient creature, I think of something that looks like that. I think of a living, breathing, fleshed out creature in full color in a paleo environment. And so paleo art is a really important translator from the phylogenetic trees, from the statistical analyses, from these papers into the public. And so I was thinking about, we have this infinite unknown that drives paleontology to be what it is. And we also have paleo art as this important link for why paleontology is in the world in the way that it is. But to bridge the two, I think that more abstract ceramic sculptures, which is my specialty, each of these pieces is named after and inspired by one particular Permian tetrapod, but there is a lot of liberty taken. And my message is not that any Permian creature looked like any of these creatures. My message is instead that there are so many forms and textures that we don't know about. And I think that through more non-traditional methods of making paleo art, you can draw upon the same wonder that inspires paleontologists and non-paleontologists alike, without compromising any of the science.
And the last one we have, at least for this video, again, not even scratching the surface of the research that was presented at GSA. I only had so much time to talk to so many people. But the last one that we have for this video is Carrie Schuster from the University of San Diego, who studies how warfare can cause heavy metal contamination of soils.
Hi, I'm Carrie Schuster, and my project is the Black Sands of Iwo Jima, leveraging the past to improve modern warfare. So in 1945, we had the bloodiest battle of Iwo Jima, which left behind a significant amount of warfare destruction and damage, which leached out a bunch of heavy metals. And so I was lucky enough to take some samples of Invasion Beach, found significant levels of heavy metals dispersed in the soil, specifically mercury, lead, zinc, and copper. And then we compared it to background samples of volcanic islands and found and attributed that all of our heavy metals are from warfare because there's been no anthropogenic activity in this area. Now, the alarming thing is this area is used heavily by the military, and military members come in and collect this sand for mementos. So when I found out that my samples were contaminated, I called my friends who took samples and I was like, my samples were contaminated. We need to test more samples and we need to put them in glass jars with glass lids so that they do not leach out heavy metals. So another thing that I ended up doing was comparing it to exposure limits of the heavy metals, but they were based on doctors looking at the cellular breakdown happening when the heavy metal actually hits it, which is lower than what our EPA and WHO limits are. So it is significant that our heavy metals are from warfare and that we need to protect our veterans that are collecting these soil samples. And then future studies should involve predictive modeling of contamination in areas of heavy metals, which can be done. And so this is my study.
So I hope you guys enjoyed learning about all of these amazing projects that were presented at GSA this year, and know that there are so many more I wasn't able to capture. But if you want to check out the diversity of research that's presented at GSA every year and potentially even contribute by presenting your own work, I highly recommend you check out next year's meeting and sign up to go. It will be in San Antonio, Texas next year, and I look forward to seeing you all there and hopefully doing another one of these videos and maybe having you showcase your research in it. Thank you so much. Bye.